Today's lesson is on short-run behavior of rational functions. And this kind of coincides with what we did last time as far as long-run behavior of rational functions. Very similar because we already found and established some of these properties. Find the zeros and vertical asymptotes of the rational function. So we know then that a zero of this equation, this rational, is found by finding the numerator zeros. So we're going to set the numerator equal to 0 to find the zeros, or the x-intercepts. And in this case, x is equal to -3, which means we have a 0 there. Now, if we want to find the vertical asymptotes, remember, all we do is set the denominator equal to 0, and there we have it, -2. So we would have a vertical asymptote at x equal -2. Now, how do we know where the horizontal asymptote is? That's leading term over leading term, which is x over x, which is 1. So we would have an asymptote at y equals 1. Here are some different things about the graph of a rational function. If we have a rational function, p of x over q of x, where with p and q have different zeros, then the long-run behavior and the horizontal asymptote, if there are any, of the rational function is given by the ratio of the leading terms of p and q. So that's very important. That is going to give us our horizontal asymptote, our HA. It's also going to give us the long-run behavior as well. So it's going to give us both of those. The zeros are the same as the zeros of the numerator. So we set the numerator equal to 0 and we solve. The vertical asymptote is also setting the denominator equal to 0 and solving. Now, like it says here, some denominators will not equal 0, so we won't have vertical asymptotes in certain rational functions. Okay, so it's very important to pause this and write those down in your notes. Can a graph ever cross an asymptote? The answer is yes, for sure. Now, it never crosses a vertical asymptote, but it can definitely cross a horizontal asymptote. You can see in this example right here that the leading term over leading term would be 1, x squared over x squared. So we would have a horizontal asymptote of y equals 1. But if we put 3 halves in for x, we also get 1. So we actually cross the horizontal asymptote here, and that's unique to rational functions. Now, it's never going to happen when it comes to vertical asymptotes. And obviously, the vertical asymptote here is going to be 0. So we have a vertical asymptote here. These are never crossing over. And obviously, you know why. Because it wouldn't be a function then, because they would probably cross over. Well, I say that wrong. Still could be a function, wouldn't be a rational function more than likely. Now, rational functions can also be written as transformation of power functions, interesting enough. If we divide both of these by q, we would get 2.5 million q to the -1 plus 2,000 from that earlier vaccine cost function that we came up with in the last video, the last lesson. So the graph of A of Q is the graph of the power function of this shifted up 2,000 units. So many rational functions can be viewed as translations of power functions. Even though they're rational written like this, they're power functions written like that. And they're the same function. Interesting. Now, this is kind of fun. Don't look at our solution here. I know you probably already did. So the graph of a rational function can give a good idea of its formula. The zeros, remember, correspond to the factors in the numerator, and the vertical asymptotes are found by the zeros in the denominator. So let's find a possible formula here. Well, let's see. We know, and it doesn't say r of x or anything, so we'll go f of x. We know it's going to be x minus 1 and x plus 3 in the numerator, right? Because we have a 0 here and here. Let's see, what else do we know? Well, we have the y-intercept. We can come back to that. It looks like the vertical asymptote is at -2, does it not? X plus 2. Now, it says squared down here, doesn't it? I'm cheating and looking. But, where's that coming from? Oh, I know where it's coming from. If y equals 1, then the long-run behavior would have to be x squared over x squared, which we have x squared in the numerator, but the leading term here is x, so we'd have to square it. Now we would have x squared. That's why it's x plus 2 squared. So this would be a possible function right here. Now we could really get into it knowing the y-intercept is -3/4. So if we said -3/4 equals 0 minus 1 times 0 plus 3. Oh, we need a k, sorry. Over 0 plus 2 quantity squared, we get, well, look at that. We get -3/4 k. So k would be 1. So this is the equation then. So it worked, just how it was. Okay, now what happens when the numerator and denominator have the same zeros? So in other words, the vertical asymptote here is 1. The zeros are, let's see, x plus 2, x minus 1, right? Oh, so this is going to be x equal 1 and x equal -2. So we have a common 0 of 1. Okay, so it's undefined at x equal 1 because the denominator equals 0 at x equal 1, but the graph of h does not have a vertical asymptote at 1 because it also equals 0 at x equals 1. So if you look at this, x plus 2 everywhere except at 1 looks just like that for x plus 2, except there's a hole at the point 1, 3 in the graph because we do not have h of 1. So if you go and look at the graph, so you need to take your calculator, and we need to put parentheses around x squared plus x minus 2, close parentheses, divided by open parentheses, x minus 1, close parentheses, zoom 6. And you will see it kind of looks like a line, I think. So you're looking at that going, well, what's going on here? Well, look at 1, 3 in your table. So go second window, start at 1, and then go second graph. You will see an error at 1. And that's simply because the function doesn't exist at 1. There's a hole there. Because it doesn't exist here, but it does exist here, so the graph actually has a little hole as it keeps on going. Your homework then is on, let's see, I didn't put the page number, did I? 11.5, apologize. It's on page 468. And it is numbers 1, 4, 5, 8, 9, 12, 13, 14, and 15. You're going to be finding zeros. You're going to be finding the horizontal asymptote, the vertical asymptote. You might be finding some holes, and then you might be finding some long-run behavior as well. So let's look at number 4. It says find all zeros, vertical asymptotes, horizontal asymptotes, and describe the long-run behavior. Okay, on number 4, it says x minus 4 over x squared minus 9. So remember, to find the zeros, we set the numerator equal to 0, so it's 4. So we know we have a 0 at 4. How do we find the vertical asymptotes? We set the denominator equal to 0. So that's going to be x plus 3, x minus 3, difference of squares. So we're going to have a vertical asymptote at -3 and +3. Okay, so that's what we got so far. I didn't even look down there. Horizontal asymptote now is leading term over leading term, which is x over x squared. Well, that would be 1 over x. So you need to graph 1 over x. You will get this. Okay? So it doesn't matter which way we approach infinity, to the right or to the left, the graph both approaches 0. So y equals 0 is a horizontal asymptote. So what's the long run behavior as x approaches infinity? Y approaches 0, and as x approaches negative infinity, y approaches 0. So the long run behavior then is 0 in both directions. All right, 12 and 13, we got a little new notation here. Letter A, the limit of x, as x approaches a from the right is how you read that. So with a equals 5 means what does the function approach as x approaches 5 from the right side of the graph? So you need to graph, so go back to y equals, clear it, hit x divided by parentheses x, or 5 minus x. Close parentheses, zoom 6, and as you approach 5 from the right, what is the graph approaching? I got negative infinity because it looks like this at 5. Okay, that would be negative infinity. Now, as we approach 5 from the left, this direction, it's approaching infinity. Okay? So we just answered B as well. Now 13 then, we will look at it and do it the exact same way.